previous lecture we had introduced the Bra and Ket algebra, the concept of linear vector spaces, and had solved the harmonic oscillator problem. For the harmonic oscillator, the Hamiltonian was given by p square by 2 mu plus half mu omega square x square. Our objective was to solve the eigenvalue equation, and this represents the eigenvalue equation, where h prime is the eigenvalue and ket h prime represents the corresponding eigenket. We had shown that the eigenvalues h prime is equal to the E n, this is equal to n plus half h cross omega, where n takes the values 0, 1, 2, 3, etc. So, we obtained the same eigenvalues as we had obtained while solving the Schrodinger equation. So, corresponding to the eigenvalue h prime, the eigenket is denoted by ket h prime. So, we denote these by h ket n is equal to n plus half h cross omega ket n. So, this is the eigenvalue, and corresponding to the eigenvalue n plus half h cross omega, ket n are the eigenkets. Now, since h is a Hermitian operator, all the eigenvalues are of course real, but we had shown that eigenkets belonging to different eigenvalues must be orthogonal. That is, m ket n must be equal to 0 if m is not equal to n. Furthermore, since this is a linear equation, any multiple of ket n, let us suppose I write ket p is equal to some multiple of ket n. Then if I multiply both sides by the complex number c, then h ket p is also an eigenket belonging to the same eigenvalue n plus half h cross omega. So, the eigenkets are determined within the multiplicative constant, and we choose the multiplicative constant such that they are normalized. So, this is the orthogonality condition and this is the normalization condition. We can combine these two and we can write m n is equal to delta m n, which is the Kronecker delta symbol, which is 0 if m is not equal to n and is equal to 1 is. So, this is known as the Kronecker delta function. Okay. So, these are the eigenvalues and eigenkets of the operator h. Now, I rewrite this equation. So, I have h ket n is equal to n plus half h cross omega ket n. We had also introduced two operators a and a bar. So, a was equal to mu omega x plus I p under root of 2 mu h cross omega, and a bar was the adjoint of this. And we had shown that h a ket n. So, if this is h prime, then this will be the eigenvalue was h prime minus h cross omega a ket n. So, if ket n is an eigenket of the operator H and the corresponding eigenvalue is H prime, then A ket n is also an eigenket of the operator H belonging to the eigenvalue H prime minus H cross omega, provided of course, as I had mentioned, that A ket n is not a null ket, because if this is a null ket, then this is a trivial equation. So, therefore, if I subtract this, so this becomes n minus H prime minus H cross minus n minus half H cross omega, A ket n. Now, we also know that if I replace n by n minus 1, so if I replace n by n minus 1, this becomes n minus half H cross omega. So, this must be a multiple of this. So, I should have A ket n must be a multiple of ket n minus 1. So, I write this as ket p, and if I take bra p, then this will be equal to n A bar is equal to C n star bra n minus 1, and if I write H cross omega bra p ket p, then this will be equal to n H cross, this is just a number. So, I can put it anywhere I feel like, A bar A ket n, and on my right hand side will be H cross omega mod C n square bra n minus 1 ket n minus 1, but since they are normalized, so this is equal to 1. Now, quite some time back in my last lecture, I had shown that this was equal to n H minus half H cross omega. I had shown that H cross omega, we had shown that H cross omega A bar A was equal to H minus half H cross omega. So, therefore, let me write down the right hand side, sorry. Is it coming all right? Yeah. Yeah. So, the right hand side is H cross omega mod C n square, and that is this. This is equal to n H ket n minus half H, this is just a number. So, I can take it out bra n ket n. H ket n is equal to n plus half H cross omega bra n ket n. So, this is 1 and this is also 1. So, this is minus half H cross omega. So, this quantity is equal to 1. So, I can, because the kets are normalized. So, this will be equal to n H cross omega. So, this factor and this factor cancel out, and we obtain within a phase factor C n is equal to under root of n. Therefore, we get the result that A ket n is equal to square root of n minus 1. This is a very important result that we must remember. Now, once again, if we start with the same equation and we start with the same equation, h ket n is equal to n plus half h cross omega, and instead of a we write a bar. So, a bar ket n is an eigenket corresponding to the eigenvalue n h prime plus h cross omega. So, this is then the eigenvalue becomes n plus half h cross omega. So, therefore, we obtain that h operating on a bar ket n will be equal to h prime plus h cross omega. So, this is n plus half plus 1 h cross omega. So, it is h prime plus h cross half h cross omega. So, this will be a bar ket n. So, a bar ket n is an eigenket of the operator h belonging to the eigenvalue h prime plus h cross omega. So, therefore, a bar ket n must be a multiple, let me write down say d n of n plus 1. So, let us suppose this is ket q, then bra q will be equal to n a bar bar, which is a, which is d n star bra n plus 1. And just as we did last time, if we now multiply h cross omega bra q ket q, this is equal to bra n h cross omega a bar ket n, this is equal to mod d n square bra n plus 1 ket n plus 1, that is a, that is 1. Now, we had in yesterday's lecture, in the lecture before this, we had said that we had derived that h cross omega a bar a was equal to h plus half h cross omega. So, this quantity is h plus half h cross omega. So, we rewrite this and we obtain mod d n square, mod d n square is equal to n h ket n plus half h cross omega n ket n. So, this is equal to n plus h operating on ket n will be n plus half h cross omega, and then there will be bra and ket n, which is 1, this is 1 plus half h cross omega. I am sorry, there is one thing that when I multiplied this by h cross omega, I should have multiplied this also by h cross omega, because I wrote bra q ket q multiplied by h cross omega. So, I missed out writing the h cross omega at the last step. So, this is your h cross omega d n square. So, this is 1 and this is half h cross omega. So, this becomes n plus 1 h cross omega. So, this h cross omega here and this h cross omega cancel out, and if I take the square root, so you will get d n is equal to square root of n plus 1. So, we get two very important relation. The first was a ket n is equal to square root of n minus 1, and the second one is a bar ket n is equal to square root of n plus 1 n plus 1. Since the operator A raises by one number the value of n, and here it lowers the value of n, these are known as ladder operators or creation and destruction operator. Now, in this case, if we write a ket 0, then n is 0. So, this is a null ket. So, this is the ground state and one cannot go below that. Ket 0 is the eigenket belonging to the eigenvalue h prime is equal to half h cross omega. So, here once again A is a non-null operator. You see, when I have two numbers, say C1, C2, if this is 0, then we say either C1 must be 0 or C2 must be 0. But in operator algebra, this argument is not valid. Here A is a non-null operator, ket 0 is a non-null ket, but A operating on ket 0 is a null ket. It is something like this: if you differentiate d2 by dx square of a x plus b, this is a non-null operator, this is a non-null function, but if you differentiate these two, this is always 0. So, here you have this a ket 0 is a null ket, which says that you cannot have an eigenvalue less than that, less than half h cross omega. Okay. Now, with this algebra, we can very easily calculate many of the quantities. For example, let us suppose we want to calculate delta x, delta p for the harmonic oscillator states. Now, what do I mean by delta x, delta p? Let me just first consider delta x. So, delta x is the x square minus x average square under the root. Now, if you use Schrodinger type of wave functions, let us suppose we have h psi n of x is equal to E n psi n of x, where psi n of x, as you recall, for the harmonic oscillator problem was n's of n nh of psi e to the power of minus half psi square. These are the normalized eigenfunctions. So, what will be my x square? I have to calculate like this: x square will be this. So, let us suppose this is psi n of x. So, this will be from minus infinity to plus infinity psi n star of x, x square psi n of x dx. These are normalized. So, actually this is divided by psi n star psi n, but we have assumed that these are normalized wave functions. Minus infinity to plus infinity psi n x mod square dx is equal to 1. So, this is my x square. Similarly, x will be just the same quantity, but x square replaced by x, and as we had discussed, the p will be minus infinity to plus infinity psi n star. I am removing, I am just, and then I must use the differential representation. So, minus I h cross d dx of psi n of x dx, and similarly p square will be minus infinity to plus infinity psi n star of x, and p square will be minus minus plus then minus. So, this will be minus h cross square d 2 psi n by dx square. Now, using the Hermite Gauss functions, it is of course possible to calculate these integrals, but it is in general they are very cumbersome. What we will do now is to use operator algebra and calculate n x square n. This is my x square. So, any operator, the expectation value of any observable will be at the in the nth state will be n o n. Let me illustrate this. First of all, let me calculate what is x average. X average will be, the average value of x will be n x n. Now, you may recall that a, the operator a was equal to mu omega x plus I p divided by under root of 2 mu h cross omega, and then a bar was equal to mu omega x, x bar is equal to x, and this is minus I p, because x and p are observables. So, x bar is equal to x and p bar is equal to p. So, divided by under root of 2 mu h cross omega. If I add them up, then I will get a plus a bar is equal to, the p and p will cancel out. So, 2 mu omega. So, this will be 2 mu omega divided by under root of 2 mu h cross omega times x. So, therefore, x will be equal to under root of h cross by 2 mu omega a plus a bar. This is the operator. So, we will have this is equal to under root of h cross by 2 mu omega n of a n a plus a bar. So, plus n a bar ket n. Now, this is very easy to calculate, as we just calculated that a ket n was equal to square root of n minus 1. So, this quantity will be bra n minus 1 and this is square root of n. So, this is 0. So, similarly, a bar ket n is equal to square root of n plus 1 n plus 1. So, this will be bra n ket n plus 1, and this is because they are orthonormal kets. So, this is also 0. So, we get the result expectation value of x is 0 corresponding to a particular state, eigenstate of the harmonic oscillator. Let me calculate x square. So, what is x square? X times x. So, let me write down the expression for x. So, this is equal to H cross by 2 mu omega A plus A bar. So, x square, the square of an operator is just x times x. So, this will be equal to H cross by 2 mu omega A plus A bar whole square. So, we must keep the order. So, this will be A plus A bar plus A bar A plus A bar A bar. One must be very careful. One must not write 2 A bar or A square plus A bar square plus 2 A bar. No, because this A plus A bar has to be operated on A plus A bar. So, this will be A plus A bar plus A bar A plus A bar A bar. Now, I want to evaluate bra n x square ket n. Now, the first term will be bra n, you can do it. So, this will be A operating on that will be square root of n A n minus 1, and this will be square root of n minus 1. So, n into n minus 1 n minus 2. So, this will be 0, because these are eigenkets belonging to different eigenvalues. So, the scalar product is 0. Similarly, A bar. So, you have n A bar ket n. This will be square root of n plus 1 n A bar n plus 1, and this will be square root of n plus 1 times square root of n plus 2 n plus 2. So, since these two numbers are not equal, so this will be also 0. So, therefore, we get the relation that n A n is 0 and n A bar is also 0. But these, the matrix elements corresponding to this, the scalar product corresponding to this will not be 0, as I will show in a minute. So, we will have A bar ket n bra n. So, this will be, please see, A bar ket n will be square root of n plus 1. It is really very simple. So, this is bra n A n plus 1. Now, this will be n plus 1, A operating on n plus 1 is again n plus 1. So, this will be n which is 1. So, this is equal to n plus 1. Let me do the other one, n A bar A ket n. So, A ket n will be square root of n minus 1, and A bar ket n minus 1 will be square root of n, because you remember that A bar ket n is equal to square root of n plus 1 n plus 1. So, if I replace n by n minus 1, so n minus 1 will be square root of n. This you must remember. So, this will be equal to square root of n times square root of n is just n. So, if I add these two, so this becomes equal to n plus 1. So, in this expression, let me therefore we had this. So, therefore, n x square n will be equal to h cross by 2 mu omega. So, this is 0. So, let me write it down, n a n plus n a bar n plus n a bar a n plus n a bar n. We have just now shown that this is 0 and this is 0, and this is equal to a bar is equal to n plus 1 and this is equal to n. So, therefore, this will be 2 n plus 1, and if I take the half inside, so we will get h cross by mu omega n plus half. So, my expectation value of x square is this, x is 0. So, therefore, delta x is equal to x square minus x average square, but this is 0. So, you will have under root of h cross by mu omega under root of n plus half. So, one result we have obtained. Similarly, we wrote down the two operators, A which was equal to mu omega x plus I p divided by under root of 2 mu h cross omega, and A bar is equal to mu omega x minus I p by under root of 2 mu h cross omega. Now, one can immediately see that in order to obtain an expression for x, we add them up. In order to obtain an expression for p, we must subtract them. So, we get A minus A bar will be, if I take out 2 mu h cross omega outside, then this will be I p minus minus I p. So, therefore, this will be 2 I p. So, I multiply both sides by I. So, you get p is equal to, and there will be a minus sign here. So, it will be under root of mu h cross omega by 2, then I, and then A bar minus A. Please see, if I multiply this by I, so if I multiply this by I, this becomes a minus sign here, and this, so this will be I, and if I take the minus sign here, then A bar minus A. So, therefore, we finally obtain that the operator, the representation of the operator P is equal to I mu h cross omega by 2 A bar minus A. Now, it is trivial, it is really, once we have done the to calculate expectation value of P and expectation value of P square. So, you have expectation value of P is equal to Bra and Ket P Ket n. So, this will be I under root of mu h cross omega by 2 n A bar n minus n A n. as we have done before, this is proportional to ket n plus 1. So, this is 0, this is proportional to ket n minus 1. So, the scalar product of that is 0. So, this is 0 and the second one is equally straightforward. So, p square will be equal to n p square. So, if I square this, I will get minus mu h cross omega by 2, and then there will be 4 terms n, and this if I multiply a bar minus a with a bar minus a. So, it will be a bar minus a multiplied by a bar minus a. So, once again we have to be very careful and we have to write them in proper order. So, a bar ket n, then this operating on this will be minus n a bar a ket n, then this term minus n a bar ket n, this operating on this will be. I hope you now realize that this term will be n plus 1 some multiple, and then a bar n plus 1 will be proportional to n plus 2. So, we will have a term which is n plus 2, which is 0. So, this term is 0, similarly this term is 0, and I can take the minus sign outside, and I leave it as an exercise for you to calculate, and you obtain an expression. So, which will be something like this. So, we can calculate then delta p, which will be equal to p square minus p average square, but this quantity is 0 and this quantity we have just evaluated. If you multiply these two out, delta p and delta x, you will get n plus half h cross. The uncertainty product is minimum for the ground state, and as we go to higher and higher states, the uncertainty product increases. This is a result which we have obtained in a fairly straightforward manner by using operator algebra. So, the operator algebra allows us to calculate the matrix elements. This particular quantity is known as the matrix element of the operator P, and one can easily calculate the uncertainty product. Now, we had, so this completes one. We had said in our last lecture, we had said that a ket 0 is a null ket, and so therefore, corresponding Schrodinger wave function will be such. What is A operator? Mu omega x plus I p by under root of 2 mu h cross omega psi 0 of x is equal to 0. So, this term goes off. So, we had obtained mu omega x psi 0 of x, and p is minus I times minus I h cross d by dx. So, I square is minus 1, minus minus plus 1. So, plus h cross d psi 0 by dx. We integrated this equation. This is a very simple integration, and we had obtained for psi 0 of x some normalization constant e to the power of minus half xi square. So, we write this as n 0, where xi is equal to gamma x and gamma is equal to mu omega by h cross, defined to be equal to, and n 0 will be gamma by root pi square root of that. If you integrate this, so it is normalization is with respect to x, that is minus infinity to plus infinity psi 0 mod x whole square dx is equal to 1, and we write this in terms of the bracket algebra that ket 0 bra 0 ket 0, this is equal to this. The relationship between the Schrodinger wave function and the Bra and Ket Dirac's Bra and Ket algebra is through the scalar product. This is a scalar product. Now, I want to find higher order wave functions. So, we now use that we have psi 0 of x, we know. I want to know the higher order wave function. So, we have a bar ket n is equal to n plus 1. So, therefore, we have multiplied by square root of n plus 1. So, psi n plus 1 of x will be equal to 1 over square root of n plus 1 a bar psi n of x. So, we will have a bar is 1 over under root of n plus 1, a bar is mu omega x minus I p divided by under root of 2 mu h cross omega operating on psi n of x. So, if I take 2 outside, so I will get under root of 2 n plus 1, and then it will be mu omega by h cross x, and this is minus I times minus I h cross. So, this will be minus minus plus and I square is minus 1. So, h cross by mu omega d of dx psi n of x. We had xi is equal to, we had written down that xi is equal to gamma x, where gamma is equal to under root of mu omega by h cross. So, this quantity is xi and this quantity is d by d xi. So, therefore, we get the very important result that from the operator algebra that psi n plus 1 of x is equal to under root of 2 n plus 1 xi minus d of d xi psi n of x. So, if I know psi n of x, by simple differentiation I can find out psi n plus 1 of x, but I do know psi 0 of x. So, psi 0 of x we know, which is equal to n 0 e to the power of minus half xi square. So, if I substitute it there, so then psi 1 of x will be n 0 and divided by n is 0. So, this is 2 into 1 2, and the first term will be xi into e to the power of minus half xi square, and if I differentiate this, so this will be xi square 2 xi by 2. So, plus xi e to the power of minus half xi square. So, this you can write as n1 h1 of xi e to the power of minus half xi square, where the general formula for n's of n is equal to gamma under root of pi n factorial divided by 2, I think. So, 2 to the power of n under the root. So, h 1 of xi, as you know, is equal to 2 times xi. Now, I know psi 1 of xi, so I can find out psi 2 of xi, and they will be automatically normalized. They will be automatically normalized, and once I have psi 1 of psi 2 of xi, then I can differentiate it again and I obtain psi 3 of xi and so on. And the final result is, as you all know, that psi n of xi is equal to n's of n h n of xi e to the power of minus xi square. And here the relationship with the kets is through the scalar product m ket n is equal to psi m star psi n dx from minus infinity to plus infinity, and that as you all know is a Kronecker delta function. So, we have now derived how to use the operator algebra to find out the eigenstates, the eigenfunctions, the Schrodinger eigenfunctions of the corresponding to the linear harmonic oscillator problem. We finally do an extremely important calculation, and that is find out the eigenvalues of the operator A. This is the annihilation operator, that is A is equal to mu omega x plus I p divided by under root of 2 mu h cross omega. I want to solve the eigenvalue equation. A ket alpha is equal to alpha ket alpha, where alpha here is a number. Now, I want to solve this equation. Now, as we had mentioned earlier, that the eigenkets of the operator H form a complete set of wave functions, that is n plus half h cross omega ket n, and Dirac argues this in a very beautiful manner, and he says that any state of a dynamical system, if you make a measurement of an observable, then it collapses to the eigenstate of the observable. Since, and therefore, any state of a dynamical system should be expressible as a linear combination of the eigenstates of the observable, and therefore, the eigenkets of the observable must form a complete set of functions. So, therefore, any arbitrary ket, say ket A, can be described as a linear combination of this. And how do I find the C n? The C n I find as, if I multiply this equation by say bra m. So, I get bra m ket A, this is equal to summation, this is a n m n, this summation is over n, this is equal to delta m n. So, when I sum over n for a given value of m, this comes out to be C m. So, I have any arbitrary ket A, if I sum over n, then C of n is equal to, so C m is equal to m. So, I write this down as, this is just a number. So, I can write this as n times C n, I can always write that, because this is a number, I can put it anywhere I like. But C n from this equation is C n is equal to n A. So, I write this as summation n n A. Now, this is a linear operator. Since this is valid for any arbitrary ket A, so this must be an unit operator. So, we say that this is known as the completeness condition of orthonormal kets ket n summed over all values of n. This is an unit operator. This is known as the completeness condition. So, any state can be expanded in terms of the eigenkets of the Hamiltonian. So, we rewrite this A ket alpha. I want to solve this eigenvalue equation. I want to solve this eigenvalue equation, and I write alpha as summation C n ket n. So, for n equal to 0 to infinity, 0, 1, 2, 3. So, let me do this carefully. So, A operating on this, C n's are just numbers. So, A operating on ket alpha is just summation C n A ket n. So, n equal to 0 to infinity, 0, 1, 2, 3 to infinity, and this will be equal to alpha times C n ket n. A ket 0 is a null ket, and A ket n is, as we have obtained, n equal to now 1, 2, 3, because n equal to 0, that is a 0. So, C n square root of n n minus 1. This is equal to alpha n equal to 0 to infinity C n ket n. Now, let us expand this. Let us write this out. So, we get C 1 square root of 1 ket 0 plus C 2 square root of 2 ket 1 plus C 3 square root of 3 ket 2, and this will be alpha times C 0 ket 0 plus C 1 ket 1 plus C 2 ket 2. And so, therefore, C 1 will be alpha by root 1, because this is a set of orthonormal kets. So, if I multiply by bra 0, only this term will remain and this term will remain. So, C 1 will be equal to alpha by root 1 C 0. C 2, now if I multiply by bra 1, so all the terms will disappear excepting this term and this term. So, you will get C 2 will be equal to alpha by root 2 C 1. So, this will be alpha. So, C 1 is equal to alpha by root 1